Greetings, physicists, and welcome to your lecture for Chapter 2, or Newton's Laws, Part 1. Now, before I go any further, let me state that I am not asserting any claims here today to disparage anyone's religious beliefs. It may very well be that science is the answer to how, and religion is the answer to why. We don't know. And that's not science to argue about it. So everything I'm going to state today is fact, things that actually happened. Once upon a time, the study of physics was not what it is today. They once called the exploration of the natural world natural philosophy. That was the ancient Greeks, of course. Now, I famously do not spend a lot of time on red herrings, so we're not going to talk too much about why Aristotle was wrong about the motion of objects. So we'll just talk about it very briefly, just a little. Okay? He thought that things moved to where they belonged and moved according to their nature. That means, where do rocks belong? They belong on the ground, right? But there's a problem. Let's say you've got a landscape, there's like a well, and there's like a hill up here, right? Something. Now, if you take a rock and you throw it up on top of the hill, it can just sit there, right? Does that mean that's its natural place? Doesn't the rock want to like move to places that are lower? If you threw the rock down here, it would sit here. If you threw the rock up here, it would probably roll down the hill a little bit, right? So rocks want to go to a lower place, right? So does that mean that all rocks belong at the bottoms of wells? That's not even the lowest they could go, right? Does that mean all rocks belong at the center of the earth? You can see the problem here, right? It's ridiculous. So this isn't about where rocks belong. It's not about their nature, right? It's really more about a combination of things. If you throw this rock up here, obviously the friction with the earth and the grass or whatever may just keep it up here for a while, right? So needless to say, Aristotle was wrong. Now, that doesn't mean that we have to invalidate all of our thoughts forever, right? That doesn't mean that the ancient thinkers didn't know anything. Obviously, they were able to figure out the shape of the earth because of our shadow on the moon, how big the earth and the sun is, and so on, right? Once upon a time, a man named Nicholas Copernicus no more invented the idea of the heliocentric or sun-centered model of the solar system than Thomas Edison invented the light bulb or Julius Caesar invented the Julian calendar. None of those things happened, okay? However, it is perhaps worth mentioning that he realized, Nicholas Copernicus that is, that he could predict the motions of the planets much better if the sun, not the earth, was at the center of the solar system. However, it was perhaps Aristarchus of Samos that came up with the idea to put his thoughts about the matter into writing first almost 2,000 years before Copernicus and the Copernican revolution, or the widespread understanding of the fact that the sun is at the center of the solar system and not us, right? We are not the center of the universe. However, Copernicus, like Galileo, was afraid that something really, really bad might happen if the church found out about his theories and his evidence. Once upon a time, back in those days, you could maybe get a visit from the Inquisition. And if the Inquisition came to pay you a visit, you were generally never seen or heard from again. Long story short, Copernicus started to figure a lot of these things out, which challenged the widely accepted at the time thought that the Earth was at the center of the solar system, and indeed the universe, because we were special, right? And so Copernicus didn't want to publish this book that he had written with all of his findings until the year that he died. He once received a letter from the Archbishop of Capua, which said, and I quote, "Some years ago word reached me concerning your proficiency, of which everybody constantly spoke. At that time I began to have a very high regard for you, for I had learned that you had not merely mastered the discoveries of the ancient astronomers uncommonly well, but had also formulated a new cosmology, or story of how the universe came to be, or at least the solar system. You maintain that the Earth moves that the sun occupies the lowest and thus the central place in the universe. Therefore, with the utmost earnestness, I entreat you, most learned sir, unless I inconvenience you, to communicate this discovery of yours to scholars, and at the earliest possible moment to send me your writings on the sphere of the universe together with the tables and whatever else you have that is relevant to this subject. Now, if you were Nicholas Copernicus, and you knew that the sun was at the center of the solar system, you had all this math backing it up, and you could predict where the planets were going to be and when, which was a major problem for the geocentric or Earth-centered model of the universe. But you didn't want the Inquisition to throw you in a jail cell and draw and quarter you or torture you to death or whatever. What would you do? You probably would do the same thing that he did, right, and not give all of your findings to the Archbishop of Capua and get a visit from the Inquisition. Nobody wants that. So, long story short, the Earth is moving. Now back then, Copernicus did not know how fast the Earth was moving, but nowadays we know that not only is the Earth rotating, right, spinning around, causing day to go to night and so on, but it's also revolving around the sun, right? But the sun is flying around the Milky Way galaxy, and galaxies are hurtling through space away from each other because the universe is expanding. And if you take all of that into account, the Earth is actually moving really fast. Now, if we're all moving so fast, how is it that we can actually interact with objects and people near us before they all fly away to distant corners of the universe? Well, that, of course, is because we're all moving together. Right now, you and I, and the computer that you're sitting in front of, the room that you're in, are not flying away from each other. Why? Well, because relative to each other, we're all moving at the same speed. The book uses the example of a bird trying to swoop down on a worm, and if everything is moving so fast, there's no way that the bird can catch the worm, right? Because relative to the bird and the Earth, the worm really isn't moving too much, and so the worm can just get swooped up by the bird. You ever try to do card tricks on an airplane? Why don't the cards just always fly everywhere all the time? Well, because relative to the airplane, you really aren't moving much, and neither are the cards. Enter Galileo Galilei, the man accredited with being the founder of modern science. Why? Well, he used things like experimentation, analysis, and hypothesis, and if you were paying attention, you know that's called the scientific method, right? He used these things to disprove Aristotle. How, you may ask? Of course, well, first he dropped objects of different masses from the Leaning Tower of Pisa, and he showed that they fell basically at the same rate. So, this is an eraser, right, for the whiteboard. This is a pen. These obviously have different masses, but if we drop them, they basically fall at the same rate, right? He even managed to show that if air was removed from the equation, that you could take two objects of crazy different masses. And what he did is he took a big bell jar, right, a big glass thing, and he pumped all the air out with a vacuum. And I think it was a cannonball and like a feather. Obviously, I didn't major in art, right? But where there was no air resistance, these two objects actually fell at the same rate. They fell together. Crazy, right? Now, Galileo, of course, being a true scientist, wanted to know why. Well, let's take, obviously, these two objects are of different masses, but these two objects, this piece of paper and this pen, are also obviously of different masses, right? Now let's see if they fall at the same rate. They very clearly did not. What happened? This piece of paper fell much slower, right? But What if I take away the reason for that to happen? Obviously, the paper fell much slower because of air resistance. Now, if I drop these two objects, the paper all crumbled up, and the pen together, they fall at the same rate. Pretty straightforward, right? Now Galileo decided that he was going to press on and build ramps. And we all know what a ramp is, right? It's just a surface that is not level to the ground, you know, from gravity. Say you've got a ramp here, right? Now, if you take a ball and you just kind of let it go, what's it going to do? It's going to roll down the ramp. And as it does so, it's going to move faster, right? What if you took the same ball and you rolled it upward? What's going to happen? It's going to roll up, and eventually maybe it's going to slow down, right? And eventually it's going to stop and maybe roll back. Why did the ball roll faster downhill and slower uphill? Is something pulling it? Is something pushing it? Why, yes, of course. Gravity, right? So what's happening? If we want to talk about just what's happening to this ball here, gravity is pulling it downward, right? Now, some of this force is going to go into the ramp, like this. Some of this force is going to accelerate this object down the ramp. And so the force of gravity, if you want to break it up into two pieces, one part of this force is going to push down into the ramp. But the ramp is going to push back, right? Because when two solid objects, two physical objects come into contact, they can push on each other. And so as the ball pushes into the ramp also pushes on the ball. And these two pieces are going to cancel out. Now, if that doesn't make any sense to you, does the ball either go through the ramp or out into space? No, of course not. So this object is not going to accelerate along these lines. Obviously, gravity is going to pull straight down, right? And so if we break the force of gravity up into two components that are perpendicular to each other, namely the force that's going into the ramp and the force that's pulling it down the ramp, these two then are actually the same. And this piece is going to accelerate the object down the ramp, right? Long story short, this ball is going to roll down the ramp because gravity is pulling it. Make sense? Now, what if we made the ramp really, really steep? As a matter of fact, what if we made it totally vertical? Okay, at that point, gravity is just going to pull it straight down, and it's not going to push into the ramp at all, right? There's no contact force, what we call the normal force. That's not to say that it's normalized or blah, blah, blah. Normal is actually a mathematical term. It means perpendicular. And so let's say we've got a slightly less vertical ramp, right? We've got a piece here. Now, gravity is going to pull down. There's going to be a piece that's going to be like this, right? This is what we call the normal force, right? Because it's normal or perpendicular to the ramp. And then this piece is going to accelerate the object downward. And the component of the force of gravity that can accelerate something is going to be greater if the ramp is steeper, right? But if it's really, really shallow, so you've got a, tiny little grade ramp, okay? Here, gravity, right? And then we've got the normal force, and then we've got this tiny little accelerating piece. Here's our normal force, or our contact force in between the surfaces of the ramp and the ball. Anyway, we call this a free body diagram. Most of the time you have a free body diagram, you can use like a block, write the letter M in it to show that it has mass, that kind of thing. And then you draw the forces on the object, the forces that are affecting it. And that's how we figure things out. We call that a free body diagram. We're going to be coming back to that again later. Now, the steeper the ramp, the greater the component of the force of gravity that's going to accelerate the object down the ramp. the less steep, the smaller it is, right? We've got a tiny little shallow ramp, and so it's not going to move really, really fast very quickly. Why is that? Well, less force is taken up by contact and friction, right? If you have a steeper ramp. If you have a more shallow ramp, more of that force is taken up by the normal force, or contact and friction. Now, a more massive object is going to be more resistant to a change in motion, and so it has more inertia because it has more mass. Meaning, if you wanted to try to push something to make it move, if this was, a bowling ball, you could probably push it. But if it was a boulder, you might have to get some friends to push it, right? Because this object, this boulder, because it has more mass, it has more inertia, and it's more difficult to accelerate. This leads us to formulate, or this led Newton, Sir Isaac Newton, to formulate his first law of motion. And that goes something like this. An object in motion with a constant velocity will continue to move so unless acted upon by a net external force. Now let's take two cases. We're talking about an object with constant velocity. If that velocity is 0, we're talking about an object that's sitting still, like the eraser. Now this thing has a constant velocity of 0. It's not moving, right? And so it's going to continue not moving unless acted upon by a net external force. Something moving in a straight line through space, for example, is just going to keep moving and moving and moving until some net external force causes it to change the way it's moving. Burn a thruster, move into a gravity well, that kind of thing. Now, there are two very key words here, net and external. Net is important because let's say you've got some object, right, and it's sitting still. Let's take this for example. How many forces are acting on the eraser right now? Well, it's sitting here on the chair, right? Gravity is pulling it down, the normal force is pushing up, right? We've got gravity here, we've got the normal force. And these two are equal in magnitude and opposite in direction, right? It's not flying up into the air and it's not crashing through the chair, right? Neither one of those are happening. So these have to be equal in magnitude and opposite in direction so that they cancel out essentially to nothing, right? Just this thing by itself. No net force acting on it. Now, let's say you had, instead of 2 forces, you had 4 forces, and those all added up to 0. You still have 0 net force. What if you had 6 forces, or 10 forces, or 1,000 forces that all added up to 0? Your net force is still 0. So what matters is whether or not the forces add up to anything, what we call the net force. Okay? Now the other key word here is external. That's important because only an external force can cause something to move or to change its motion. You can grab your shoelaces and pull yourself by them. But you cannot do that and expect to levitate. That's called an internal force. If you apply an internal force to yourself, maybe you'll rotate. If you grab yourself by your shoelaces and pull hard enough, you may fall over. But you cannot levitate as a result. That's not how that works, right? So, net and external, keywords. So it seems pretty important that we understand what we mean by a net force, right? First of all, what does a net force do? It causes a change in motion, right? Either the thing standing still or the thing moving in a straight line with a constant velocity can change its velocity somehow with a net external force. Now we're going to need to describe a few what we call basic vector phenomena here. And in order to do that, we're going to have to define what a vector is. Are you ready? Vectors are a very complicated, very scary mathematical concept. Ready? That's a vector. That's it. A vector is just like an arrow. Now, I want you to tell me what the difference between this vector and this vector is. They're pointed in the same direction, right? One is longer than the other. We say one has a greater magnitude. Now, we're going to pretend, for the sake of argument, that this next vector I'm going to draw has the same magnitude as this one, even though it might not. They're close, right? Okay, assuming these two vectors have the same magnitude, what's the difference between them? They're pointed in different directions, right? Therefore, in summary, vectors, vectors have two major quantities, qualities, whatever you want to call them. And those are magnitude and direction. There are some quantities that have magnitude but no direction, like a number of apples or something like that. That's called a scalar. That's not a vector. It's slightly different. Okay, that's great. Why do we care? Well, there are lots of useful quantities in the universe that are vectors. Let's start with the basic one, position. How do you describe the position of something or someone? Can you describe your position right now? If you were to try to describe your position right now, could you do so without describing the position of something else first, what we call a reference point? Well, let me save you the trouble. You can't. It's not possible. Try to define where you are right now. You're sitting in your chair, you're in your room, you're in your house, you're in San Jose, whatever. You can only define your position relative to the position of something else, right? So, we have to talk about a magnitude or a distance from something else and a direction. You're on top of your chair, right? You're in your room, which is in the back of the house. You're in San Jose, which is on the west coast, etc. And so you can only define your position with a reference point. Now, some vectors and the unit that we use them with. The first one was position. Now, if you want to try to talk about your position, what is the right unit of measurement to use? If you wanted to say you were, 2 meters from the back of the wall or whatever, obviously the unit that you would use is meters. And so the correct unit that we use for distance, for the measuring of distance, is a meter. Obviously, sometimes you want to use like a centimeter for something small, millimeter for something smaller than that. You use a kilometer for like the distance in between your house and your friend's house, or several hundred kilometers for the distance between two cities, or what have you. Now, if something is moving, it's changing its position, right? We can describe this change in position as a vector called velocity. Some velocities are big, some velocities are small. Thus, time is a factor. If some object moves really fast, the distance is distance over time. If something moves really fast, it moves a really fast distance, right? It changes its position or its distance really fast over a small change in time. If an object moves slower, then it changes a smaller distance, or changes its position less over the same time interval. Now, what could possibly be the units for velocity? Well, the units for position are meters. The units for time, usually we use something like seconds. So, the basic unit for velocity is something like meters per second. Probably the unit that you're used to using for speed is probably more like, or velocity, excuse me, is more like miles per hour. That's the one you see in your car, right? But miles is still a measurement of distance, and hours is still a measurement of time. It's the same thing. But generally, we don't use miles per hour in science. We use something like meters per second. That's better. Now, if you look in your car as you're driving, and you look at the speedometer, and it tells you your speed in miles per hour, is it telling you your velocity? It is not, because your speedometer doesn't tell you your direction or where you're going. For you to know your velocity, or the velocity of some kind of object or whatever, you have to know not only the magnitude of the speed, right, how fast it's moving, but also what direction it's going in. So, in order for you to know what your velocity is, you have to know where you're going also. So if you have like a compass, or at least know you're headed northbound on 101, something like that, you can actually know your velocity. Excuse me. Now, your velocity can of course change. You can speed up or slow down, you can turn the wheel, those kinds of things. If you change your velocity, you are accelerating. Therefore, acceleration is a change in velocity. So, acceleration is change in velocity with respect to time. If you're in your car and you hit the gas, right? Let's say your car is moving this way northbound on 101. If you hit the gas, the velocity is going this way. What way are you accelerating? Well, you're accelerating forward, right? What about if you hit the brakes? In that case, you would be slowing down, right? You would be accelerating backward. What if you turn the wheel? So you turn the wheel and you neither speed up nor slow down. That means you would be accelerating perpendicular to the direction that you're traveling, right? And that would cause you to turn like in a circle, right? You would turn the car. Now, if you're turning the wheel, do you change your speed, the magnitude of your velocity? How much is that changing? Maybe not so much. You're really just changing the direction at that point, right? But any change to velocity, whether it's the magnitude, speeding up or slowing down, or the direction, turning the wheel, right? You are accelerating because you are changing your velocity. You can accelerate very quickly, like free fall, or you can accelerate slowly, like down a very shallow ramp. I almost used the word narrow. So velocity can increase more or less with respect to time. Thus, what are the units of acceleration? Well, if you're changing your velocity, right, velocity is meters per second. The unit of time is seconds. That's meters per second, or meters per second squared is usually how we write it. So how does an object accelerate if more than one force is acting on it? Well, we have to use this thing that we call vector addition. And I know that sounds scary, but it's actually very straightforward and something that we've all done plenty of times before. Let's talk about adding two vectors. Let's say that you have some object, right, some mass, and you apply a force here, but you also apply a force this way. How does that work? Well, if you just take this vector, we'll call this, let's use v for vector. Let's call this force 1, we'll call this force 2, right? You take force 1, and then you add force 2 to it by sticking one vector on the end of the other one. And then this one is the total. From the start of the first one to the end of the last one. That's the total force applied, right? That would be like saying if you pulled this way and pulled this way on this object, you'd actually be pulling somewhere in between. Makes sense, right? Now let's take the simplest possible case where you have two teams playing tug of war, right? Here you have some rope. And one team pulls with a force of 50 newtons this way, and one team pulls with a force of 50 newtons this way. We all know what happens, right? The net force is 50 minus 50, you get 0. And if that happens, then the two teams are in a stalemate and the rope doesn't move, right? Until somebody gets tired or gets a better grip, digs in deeper to the ground, whatever. Now, what about if one team pulls with a force of 50 newtons and the other team pulls with a force of 45 newtons? Well, we can very clearly see that this team is going to win by 5 newtons, right? That's the net force on the rope, right? Now this is really easy because these directions are opposite each other, what we call anti-parallel. But what if you have two or more forces that are acting on an object that aren't parallel or anti-parallel? Well, what about if they're at, let's say, you've got one force here and one force here. Well, if this is force 1 and this is force 2, you can make a parallelogram. Here's force 2, here's force 1, right? Add these tip to tail, or we can add them tip to tail the other way. And then this here is 1 plus 2, or the net force, right? We call it the parallelogram method. Now sometimes you may have two forces that are applied to an object, and these forces are perpendicular to each other. We'll call this force X and we'll call this force Y maybe. Now, if you wanted to know the total force, we'll say this is X, we'll say this is Y. Is there a way to figure out how big X plus Y is? Well, if these are at right angles to each other, we can use this thing called the Pythagorean theorem. Now let's say that X is 4 and Y is 3. How big is X plus Y? Well, in order to get this, we have to say X plus Y is equal to the square root of X squared plus Y squared. X squared is 16, right? 4 times 4 is 16. 3 times 3 is 9. So we're talking about the square root of 16 plus 9. That's the square root of 25. That's 5, right? So X plus Y is 5. That's the Pythagorean theorem. Now this only works, of course, if two forces are at right angles to each other, right? And you could kind of say that this force X is the X, or the horizontal component of the net or total force, and force Y is the vertical component of this net force, right? They are perpendicular to each other, and so they are the perpendicular components of the net force, or the resultant, whatever you want to call it. Now, if all the forces on an object add up to 0, the object is said to be in equilibrium, very much like the tug of war with all the ropes of the two teams pulling exactly as hard on each other. The net force on the object is 0. If the force is at 0, the net force, then Newton's first law says the motion of the object does not change. Another way of saying that is that the acceleration is 0, so it neither speeds up, slows down, changes direction, or changes its motion in any way. Now, I hinted at this a little bit earlier. We talked a little bit about the normal force, right? And I'm going to use our friend the eraser again here. There's my awesome drawing of the eraser, right? Just a box with the letter M in it to show that it has a little bit of mass, right? Now, why is this thing not falling to the center of the Earth? Well, because this thing is on the chair, and the chair is pushing it up, right? We call that the normal force. Obviously, the force of gravity is still pulling it down. Obviously, these two are equal in magnitude and opposite in direction. This object is neither falling through the chair or flying out into space, and so these forces add to 0, right? The normal force and gravity, therefore, must be equal in magnitude and opposite in direction for this object to remain in equilibrium. Now we call it a normal force because it is always normal or perpendicular at a right angle to the surface that it's on. Here, the normal force is pointing away from the chair, right, in the opposite direction of gravity. The same applies to a mass on the end of a slinky, for example, right? Now, can an object in equilibrium be moving? Well, yes, of course. What if you're driving in your car, right, and you're using up just enough gas to keep your car moving? Here's my awesome drawing of a car, okay? So you've got some velocity moving forward, right? Let's say you're moving at, I don't know, 65 kilometers per hour, because we don't use miles, okay? So you're driving your car and you keep moving at 65 miles per hour. The force of the engine speeds you up, right? So you've got the force of the engine pushing you forward, right? Speeding you up. But then also there's going to be a force of friction with the road slowing you down. But if you're going at this constant velocity, then these two have to cancel out, right? The force of friction and the force of the engine. One is speeding you up, one is slowing you down. But if you're moving at a constant speed, they have to add up to 0. That means if you were to sum, apologies, if you were to sum up all the forces, right, the forward and the backward one, or the engine and friction, you would say that they sum to 0. I hope you have enjoyed this video. I'll see you soon for Chapter 3.